Hello again and welcome back to my computer vision channel. Today we will talk about Grounding Dino. This is the model that deals with the so-called open set object detection. That's when instead of having a fixed set of objects ahead of time on which you train, like Coco dataset, you just train using images and text, which allows you to easily generalize to novel categories like ears, lions, benches, as well as detecting objects using so-called reference sentences. For example, the lion most to the left, which is quite useful for collaboration with, for example, Stable Diffusion, if you want to replace an object with a different object. Open set object detection allows you to just use the model without fine-tuning, without a lot of machine learning knowledge, basically, to solve your problem, because it's highly unlikely that you would need to detect something from the original Coco dataset categories, which is just 80 of them. Having a model that just understands text is much more useful. In addition, techniques used in the model to create this interaction between text and image, the so-called cross-modality features, they are, I believe, used in a lot of other models, such as GPT-4 and Stable Diffusion, to let the model just read the image and explain it using text, or to generate an image using text prompt, and so on. So knowing these techniques unlocks a lot of other possibilities for your understanding. Today, we will mostly be looking at my presentation and some diagrams and some slides from the paper. First, we will overview the two main components of Grounding Dino model, that is Dino itself for object detection and Bert for working with text. We will look at the main components of the model using my diagrams, such as the cross-modality feature enhancer, text-based query selection, and then cross-modality decoder. We will look at training datasets, the sort of input that was used to train the model, and finally we'll look at some results. Here are the prerequisites to understand what is going on here. So Grounding Dino, as well as Dino itself, is built on a foundation of series of models, starting with Decoder and then improving on top of that. There is deformable Decoder, tab Decoder, denoising Decoder, and so on. We'll not go too deep into a lot of these concepts, so I would say that just knowing how Decoder works is enough. In addition, we have this text part, and the actual text backbone is going to be a Bert. It's also nice to know what are transformers and multi-head attention, because we're going to take the same concepts and sort of expand on them a little bit to create this cross-modality image and text feature enhancer. Okay, so let's begin. First, I want to reiterate on the model itself, like why are we doing this? So before that, in typical object detection, you'd always have some sort of fine-tuning dataset like Coco, and it will have a fixed set of classes. So in Coco dataset, there's something like 80 of them, which includes person, train, bowl, pizza, cat, dog, and so on. And it doesn't include, for example, a lion. So it is quite limiting. For any practical purpose you might imagine, you would probably need some sort of different data set, and you take an already pre-trained model and then fine-tune it on your own data set. And that is quite limited because, first of all, you would need an actual machine learning engineer to do that. You'd need to get some data from somewhere, and quite a lot of it, to make the model work well enough. And it would also need to sort of keep experimenting, keep making sure that the learning rate is adequate for the size of the data set you found, and so on and so forth. Having a detector that can just generalize to other categories is really useful. You can just ask it, what is it a lion, and it will just answer or detect a lion. So in that sense, it allows you to more easily just take a pre-trained model and apply it to something else. This will also work for something you wouldn't even imagine being a category before. So for example, what if you wanted to detect lion ear, for example, or other body parts or something else? In addition, we might want to just point to a specific object using the so-called referring expression. So to say something like lion most to the left, and the model will detect the correct line. So these are the goals that we have for this model. Now let's see at how to actually implement. And let's start with the quick overview of image and text backbones that we have for the model, the Dino and Bert. So this is the diagram for the Dino. We receive an image as an input. Then we pass it through a backbone. And in our case, that's a swing transformer, which basically will divide it into patches, project down using single convolution to convert just raw pixels into embedding representation. Then we'll have a series of shifted window attention operations that will take a window of several patches and just apply attention within that window, and then shift the window and apply attention again. And then it also has patch merging operation, which is the thing that basically reduces the pixel-wise dimensions of the image, but at the same time increasing the embedding size and basically creating more processed representation. So for the actual grounding dino, we'll stop here right after the backbone input. But the concepts of grounding dino are somewhat close to the original dino, so let's go over them. So the output of this backbone is this lower resolution, more refined version of the image, basically a huge embedding corresponding to each pixel that encodes detections of some useful objects, which might be, I don't know, dogs, cats, cat heads, maybe specific letters, maybe specific forms like circles and squares and so on. In addition, since we use deformable attention, which is linear to the sequence length we pass to the transformer, we are allowed to have greater sequence length. So we can just take several intermediate scales as well, and that is called multi-scale. So we basically take these several different resolution versions of the image and just flatten it all out and pass the transformer. The main thing why that is needed is because for the detection, we actually need high pixel resolution to make sure that the bounding boxes we draw are actually good enough and precise enough, which is especially important for really small objects. So if your input image is already low resolution, you're sort of, you don't have that from the very beginning. No matter how good your detector is, if input resolution is low, you're not going to get very accurate bounding boxes. So to pass that through the actual transformer, we need to flatten it all out. When we do that, we lose all the positional information, so we add positional embeddings. In case of multi-scale, we also use level embeddings that tell us from which scale, resolution scale, the pixel is coming from. Then we have our typical transformer encoder. So we have our input flattened patches of the image that are just tokens at this point. We pass them through a series of encoder layers. The output of encoder layer is the same shape as the input, so you can just consider this as refining the representation of the image to create a better representation. Then we have decoder. Decoder starts with a different shape. So if encoder would start from this flattened pixels of the image itself, and for deformable attention, it's typical to have sequence length of up to 20,000. Decoder starts with basically queries which are used to detect objects, and in case of Dino, we'd have 900 of them. One addition of Dino is to select these queries dynamically. So they are proposed by encoder output, which is basically saying that encoder itself is a version of object detector. So every output token has some understanding of where the objects in the image might be. And so we use our classification head projection to basically create bounding boxes out of these embeddings, and class predictions, and then we select top of them, maximizing the predicted probability of a class, and just use bounding boxes from that as decoder inputs. And again, in Dino, it was called mixed query selection. So we select bounding boxes for decoder input as dynamically as output of the encoder, and then content input queries are just static trainable parameters independent of the image itself. Then we have decoder, which is based on cross-attention. So we get these queries that represent basically content understanding of this specific expert, object detecting expert, as well as bounding boxes. We pass them through a series of cross-attention layers where query input for attention comes from these queries, and then key and value come from encoder output. And we get the refined predictions for objects. So embeddings, which we can project to bounding boxes and class predictions. So in normal data-like models, we have this Hungarian matching, where each of these predictions is matched in some way as to maximize the loss. So out of 900 predictions, maybe you'd have one prediction that detected this dog really well, and then one prediction that predicted this cat, and the Hungarian matching algorithm will find the perfect match. And then all the other 998 will have to be connected to the special no-object class and basically penalized for trying to detect something that was already detected by someone else. And the major thing here is to avoid duplicates in the output. In addition, and that is another thing that came from Decoder and used in Dino as well, is this query denoising, which basically helps with the training. So with Hungarian matching, we have some instability in what is getting connected to what, and because of that, training is quite long. With query denoising, we just have one query input that gets connected directly to query output. And input, instead of coming from this encoder output, it is actually generated using ground truth. So we take ground truth object, let's say this dog, we add some noise. So we basically modify the bounding box a little bit to make the task changing for the model. And then we ask the model to remove the noise, hence the denoising. So long story short, Dino is an object detection model, which means that the input to that is just an image. And then the output is a set of detections, 900 of them, detection being a class and the bounding box, so x, y, width and height coordinates. And the class is basically, in the model itself, the class is just a number from 0 to 80 in case of Coco. So it encodes a specified classes, person, dog, sheep, train, pizza, and so on. One of them being a special one called no object. Because of course, if we have 900 detections, most of them will not actually correspond to real objects from the predetermined set. This is a short diagram of Bert. So Bert is a text model. It receives just a sentence, and sentence is usually preprocessed to add special tokens such as CLS and SEP, not really used in what we are about to do. Then text is tokenized, basically splitting the sentences into words and maybe pieces of words for really rare words or tokens like NVIDIA T4 GPU, something like that. There's also this segment embedding that is, again, not really used here because we always have just one segment, so it's not really doing much. Obviously, we also have positional embedding. So after tokenization, we get just token IDs as the output. Then we look them up in some sort of embedding table, again, converting them to embedding. So basically every word, every piece of word gets its own vector representation, at which point we are back to the same input we had in Dino, just a sequence of tokens. In case of Dino, because in case of Grounding Dino, because the input will typically be quite small, we actually need just 128 or 256 sequence length. That is passed through a typical bidirectional encoder. So it uses full pairwise self-attention, where every token attends to every other token to the left and to the right. The complexity of that is quadratic to the sequence length, which is not a problem for us because in our case, the sequence is quite short. The output of that is again the same shape of a sequence of embeddings, which in original Bert might be then projected to something else, like prediction of how positive or negative this text is, or masked language prediction. In our case, we don't really need anything apart from just the raw embeddings. So this is where we stop, just the output of sequence of vectors, and that will be used in the Grounding Dino model. So once again, input is just a text. This is an example of the actual prompt that can be used in Grounding Dino, and output 128 text token embeddings after being processed by the Bert model. So they are more refined, they already contain a lot of information about what this text actually means. Now let's look at the actual Grounding Dino. So here is the actual diagram from the paper about the model. So here we have our input text as well as an input image. So text is processed by this Bert text backbone. Image is processed by our image backbone, Swing transformer. Then we have both of them, image and text features. Since both of them are now in the same basically shape, so they are both represented as a sequence of embeddings, it is relatively straightforward to create this cross interaction between image and text features. And in case of Grounding Dino, that is happening on 3 levels. So first, that's the feature enhancer that basically improves the understanding of both text and image using this cross-modality information. Second one is language-guided query selection, when we select the queries using the text input as a reference. And then we have this cross-modality decoder. And in all those 3 we'll talk about at length in a bit. But then the actual output is quite similar to Dino. So we also have a set of detections. The detections themselves contain the bounding boxes and the actual text for what the model is seeing. And in training, that is then matched to ground truth using the same Hungarian matching loss. And then during inference, we don't really use Hungarian matching loss. We just take the outputs and just use them as is. To reiterate, now the input is an image and a text prompt. And the prompt can be just one object that we are interested in detecting, say a sheep. It can be a dot-separated list of objects we are interested in detection, so a sheep, a dog, a person, or it might be a reference expression like sheep most to the right, or the man standing, or something like that. Now, one really important thing to understand here is that the output of the model does not generate new text. So instead, given the prompt, the output of one detection query is basically a set of indices of tokens in the input that this particular query has selected. So given a prompt, a sheep, a dog, a person, one output head might detect a dog. So it is not generating new text. This technique is actually similar to how Bert is used in a lot of tasks like question answering, where it does seem like it's generating text, but it's not. And it's actually much easier. So all the generating models, they perform this next token prediction, where you have some input, you predict next token, you add that token to the input, you predict another one, and so on and so forth. It's quite hard to imagine how that will work if we are predicting several objects at the same time and we need to generate some text for all of them. So this sort of token index prediction task is much simpler. So we have single pass through the model. The output of the model is this fixed set of detections, and every detection basically predicts logit probability of every token in the output to match to the ground truth object. So it will say something like a sheep has 0 chance of matching an object, a person has 0 chance, and then a dog has a very high chance of matching. And then a different head might predict a sheep instead, and bounding box for the first one, and then another head might predict a different shape. So it might say that it's this one. So the highlighted text, the predicted tokens would be the same, but then the bounding box will be different. And then again, similar to Dino and Decoder, it might not highlight anything. So it might say that that's not an object. And most of the predictions, most of the 900, will obviously be no object prediction. This sort of prediction of text as highlighting in the input also puts quite a significant limitation on the sort of prompt that you can use. You cannot just say, hey, here's a picture, just describe me what you see. Unlike GPT-4, this is not what you can do with the Grounding Dino model. You have to provide the answer within the input prompt itself. And so one way to use that, if you're just doing object open set detection, and you know which categories you're interested in, you just list them all out, separated by the dot. So you say a sheep, a dog, a person. So full Coco detection might be performed by just concatenating all the 80 categories. That actually fits in the input sequence length just fine, so it's fine. Or you provide a reference expression or several of them. So you might say a sheep most to the right, a sheep most to the left, and then the model will detect both of these, but not the sheeps in the middle. But once again, you cannot just say, hey, describe what you see on the picture, because the prompt has to contain the answer. Now let's go over our text and image backbones one more time. So we have Bert, and now we know that the text prompt used as an input will look something like this. So it can be dot separated list of categories we want to predict, or referring expressions, or something else. Because of this, because of the requirement for the prompt to contain the answer, we also use this special attention mask to separate different categories from each other. So basically, if we're doing something like detection for Coco, we might have just 80 words listed out. And we do not want to confuse Bert into thinking that we have some image that contains all of them. And because of that, we basically have the separate groups of attention used in textual representation processing everywhere. So in Bert itself, in cross-modality feature enhancer, and so on, which is basically saying that as soon as we have this dot in the prompt, that separates the part of the sentence. And so this a sheep sentence will only attend to itself, then a person will only attend to itself, and so on and so forth. So this helps not confuse Bert and text transformers into what is actually going on. So we use 128 sequence length for the text input. We have this special attention mask and obviously positional embedding. So if we look at the original paper, they don't really explain that much into what sort of prompts work better or worse. So they have this paragraph about subsentence level text feature. They have this diagram about the special attention mask in the encoder that separates different sentences so as to detect several of them at the same time in single pass, but not confuse the model. So it's really quite murky. I do believe that it actually affects training and usability of the model a lot, and it is certainly underexplored at the moment. So if we look at the source code for Grounding Dino, they didn't release the training code yet, so we'll not be able to actually look at the datasets used and the specific types of prompts they use in training, which is quite unfortunate. Then we have our image backbone, which in our case is never going to be ResNet. They just switch to using swing transformers all the time. Because we use deformable attention, we can allow really, really high sequence length. So we have multi-scale, we have something like 20,000 sequence length from different scales that get flattened out and again pass through the transformer, as well as positional encodings and level encodings. Now let's talk about cross-modality feature enhancer. So we are getting to the juicy part of the video about the actual cross-modality text to image and so on. So again, this is the diagram of Grounding Dino. We started with text and image. We passed that through the text backbone and image backbone, at which point both of them are now represented as sequence of embeddings. And then we have this cross-modality feature enhancer. They actually had a diagram about how it works in the paper. I think it does not really represent reality, at least as written in their own code. So I've made my own. So here is how it looks like. So we have our text representation at the bottom and the image representation. Both of them are now sequences. And it's just really convenient to just plot the actual potential shapes of how that might happen. So in image, because of deformable attention, we have really long sequence of 20,000 elements. And then for text, we have just 128 of them. And then embedding dimension in both cases is 256. So in all the multi-head attentions we've seen so far, you always have query, key, and value. And the first two are used to create attention matrix. So in our case, we use text for keys and then image for queries. It doesn't really matter which one for each. They are quite symmetrical. And so we just compute the dot product between these to get the attention matrix. And the attention matrix is not square, so it's not symmetric. It has 128 as one dimension and then 20,000 as 20,000 as another dimension, which is fine because this is how we are going to use that. And so then we take the value projection from the image, for example, and it has dimensions of 20,000 by 256. And so we can multiply it with the attention matrix. And by the rules of matrix multiplication, this common dimension basically cancels out. So we get this 128 times 256 as the output. And this happens to be exactly the same shape as the text input. So this is going to be the new text output. It might seem a bit weird that for text output, you actually only use keys from the text itself and then query and value from image. But if you remember how Decoder works in data-like models, for example, this is exactly the same. So the shape of the output is that of the text, so we consider it to be the text, although by this point, it basically contains information about text and image at the same time. And then for image output, we have the same. So we have this attention matrix, 128 by 20,000. We use text vectors to get this different value projection with slightly different dimensions. We have to transpose one of them. And so then this 128 dimension gets canceled out. And what we get as an output is the new image sequence. And so this is the new image output. So it's quite symmetrical. It works quite similar to the normal cross attention in decoders. The output of that layer is basically the same shape as the input, which is really convenient. So you can stack on a lot of them on top of each other. And then, as is typical with attention and multi-head attention, we also have self-attention on top of this cross-modality attention layer, where everything just attends to itself, and so on. And again, we have some dense layers, residuals, all the typical stuff that we have in transformers. So to reiterate, we have our attention matrix, which is basically a key projection of text sequence times query projection of image sequence. Then we use that same attention matrix twice. So first we multiply value projection from image by this attention mask and we get the text output. And then we multiply the value projection of text to get the image output. So once again, to get the text, we've basically used the image sequence twice as value, as query, and actual text sequence only once. And then to get the image output, we've used the text input twice as value and as key. And then the image input was only used once. Another interesting detail about what sorts of attention mechanisms are used. So for image self-attention, which has 20K sequence length, in this cross-modality layer, in the self-attention part, we use deformable attention, basically because we cannot afford 20K sequence length. We cannot afford full pairwise attention at this point and have 20K squared complexity. For text self-attention with just 128 sequence length, it's okay to have full pairwise attention, so we have that. And then in image to text cross attention, which is now 20K times 128. Again, that is not as big as 20K squared. So again, we can afford to use just full pairwise attention at this point. Now let's talk about language-guided query selection, the second cross-modality part of the model. So again, here is the diagram. We had text and image coming from the bottom. We had this cross-modality feature enhancer that basically creates the representation of the same shape as the input, but now with a lot of information exchange between text and image, creating a more refined representation of both text and image. And then we have this query selection. So the purpose of query selection is to create adequate inputs to the decoder. And so we have this query selection selecting stuff from image features, basically. But also we have this text features coming from the side. So let's see what all of that is about. So first, I just want to show how query selection worked in the original Dino model, not the grounding one. So again, we had this refined representation of the image. And then what we did basically was apply a classification head on top of that, which is basically the same one that is used to generate final predictions of the model. So we have our sequence of embeddings. We pass every embedding through this classification head, which is in the simplest way, it's just a matrix of parameters. And then we get these class predictions for 80 fixed COCO classes. And then every predicted probability basically states what is the chance that this particular pixel has detected this object. So we basically select top 900 of them to create this query input to the decoder. So here it is how it looks like in the Grounding Dino. So now we also have these processed image pixel embeddings, the 20,000 of them, and like each token is an embedding at this point. But now we don't have a set of fixed classes. So depending on what the prompt is, the model might predict different things. So instead of this fixed matrix of parameters to project the embedding that we had in the transformer down to probability predictions that we want, instead we do the matrix multiplication to text token embeddings. So this part is the same output of this enhanced cross-modality feature enhancer. And so they have this common dimension of 256, the embedding dimension. And so matrix multiplication of this one times this one gets this 20,000 by 128 predictions, right? So this is basically saying that each of the 20,000 pixels is going to predict probabilities for each of the 128 text tokens. And so what we do then is select top 900 by this probability, basically saying that every pixel has detected something. Let's select the ones that predicted something with the highest probability. And prediction here is basically the highlight of a part of the text input. And so we'll have 900 of them. Similar to how it is done in Dino, and this is called mixed query selection, we basically use this text classification part to select which sequence elements are selected. And then we take initial embeddings of these elements and actually project that down using bounding box parameter matrix to create bounding box logics. And the actual content input to the decoder is again static, just a trainable matrix, not dependent on the image, not dependent on the text itself. So this process is really similar to what we had in Dino. The main difference is basically swapping out this fixed prediction head for 80 classes with this dot product with dynamic text tokens, because text prompt can be different each time. So again, to reiterate, as an output of this cross-modality feature enhancer, we have image sequence, which is really long, and then text sequence, which is moderately short. We compute token logits as dot product between them. And don't worry if you think that it's the same operation as attention. It actually is. So this dot product is the same as we've used to get the attention matrix. So, and the dimensions of these is exactly the same as for attention matrix. We just use it for different thing now. Then we choose top 900 sequence element, and then we get the initial vectors of these sequence elements and then project that down to 4 bounding box coordinate predictions. And so these bounding box predictions are used as inputs, as anchors for the decoder, and the content input of the decoder are again not dependent on encoder, not depending on the image, are just static trainable parameters. Now let's talk about the final third cross-modality part of the model called cross-modality decoder. So once again, we've passed, we had our text and image passed to the text and image backbone. We had our cross-modality feature enhancer to just refine the understanding of image and text. Then we had our language-guided query selection to select input anchors for the decoder. And then we have cross-modality decoder, which once again receives this query input from language-guided query selection, but also looks up the output of the feature enhancer on every layer. And so in this case, the diagram from the paper actually made sense, so we'll just stick with it. If you look at this from a computational standpoint, this part is exactly the same as in a typical decoder in a data-like model. So you have your queries coming as an input, you perform some self-attention, and then you use query sequence as query for the attention layer, and then key and value come from encoder output. So you have your encoder output passed in from the side. You use key to multiply it by the query to get attention matrix, and then you multiply it by the value, again coming from this side input, to get your new output. And so this part is exactly the same as you would see in Dino or in the original Decoder. And now we can just simply add text here as well, because you can see that the shapes here and here are different anyways. So from computational standpoint, you can just add an extra layer where now instead of image features, you use text features and then perform basically the same computation. So again, the output of this one had the same shape as the query sequence. And so you can perform the same thing, getting query from here, key and value from here, calculating attention matrix, multiplying value with the attention matrix to get this new representation of query sequence, but now enriched using text information. And then obviously, again, feed-forward network, residuals, all that stuff. So another way to look at all of this is basically consider that this query input, the 900 queries are like expert, each of them being tasked with predicting a specific object. And so we had this language-guided query selection to create initial anchors, which are like areas in the picture where this particular expert should focus on. And this is not just me talking, this is actually how it's used in attention. So anchor box is used to modulate attention, controlling where the network pays attention to. And so one of the experts might be focusing on this region, another expert might be focusing on this region. Then they are basically, the self-attention can be interpreted as something like experts talking to each other to make sure that two experts do not predict the same thing and to exchange information. Then you have this image cross-attention, basically allowing every expert to look at the original image and actually refer to what is needed to be detected. Same for cross-attention with text. That's when each expert basically looks at text and again, like decides what it is that we need to predict. And that happens layer by layer. So after every layer, initial anchor is improved, creating a better understanding of where the object is, and so on and so forth. So this decoder is basically needed for refining the actual object detection on the picture. So the output of the decoder is the same shape as input. So we have 900 queries being the outputs of the model. We get bounding box predictions, but by just applying this bounding box prediction head to every query. And to get the actual token predictions, once again, we use the same process that was used during query selection. So we have our decoder output, now 900 queries, each having an embedding. And we multiply it with text token embeddings coming from this feature enhancer encoder. So multiplication basically gets rid of this dimension. So we have, for every of the 900 query predictions, we have 928 token logits. Each logit basically corresponding to the probability of this specific token being highlighted in the input. And so the output of one query is basically saying that, from this original prompt, I have detected something that matches just this token representing person. And then the same embedding projected down using bounding box head gives the actual bounding box coordinates. And then coming back to our Grounding Dino diagram, so these bounding box predictions and text token probabilities are then again passed through the Hungarian matching laws, through the denoising laws, all of that. Unfortunately, I don't have the training code for that, so I cannot say for sure. But from my understanding, this happens in roughly the same way as it was in the Dino itself. So this was it regarding the model itself. Now, since we know more about the model, about what sort of input and output we expect from it, we can also talk a little bit about training data. Again, this is a bit murky because it was not open sourced, so all the data I have is from the paper and from what I could find. Nevertheless, it's quite interesting. So again, we need input images, we need prompts as an input, and then some sort of ground truth matching between image objects being on the image matching to specific bounding boxes and specific parts of that prompt. And so what we can use is something like Coco dataset, although it does not have everything we need. There's also an analog to that called RefCoco and some other datasets, which specifically target these reference expressions, something like saying, the line moves to the left, for example, or the man standing, and so on. And then finally, we have this third one called caption data, which basically uses Bootstrap Grounding Dino model to annotate further data for training. So first of all, if we look at the Coco itself, it has quite a lot of useful info. So apart of just detection boxes, it actually has data about segmentation, so where each pixel belongs, about different instances. It also has this text description of the image. Unfortunately, it's not really bound to a specific object. It just describes the picture as a whole. So we cannot really use that to train Grounding Dino. Still, we can use Coco dataset to train this specific type of prompt. So we can just say, okay, we have fixed categories. Let's list them all out in text. So we actually convert these IDs of categories that we use in the Coco. We convert that to text somehow, and then list them all out as a prompt and let the model detect that. And obviously we have the matching for every object to a specific bounding box, to a specific part of the prompt in this case. Good thing about this approach is that we can now merge several data sets containing different sets of categories, because now the model just deals with text. We can easily merge different data sets like Coco and objects 365, for example, which have different sets of categories. We can just merge all of them together and train on them at once. There are specific data sets for reference expressions. So this one is RefCoco. There's an interesting paper behind that on basically gamification of annotation, allowing just random people from the internet to play and to generate these reference expressions and match them to bounding boxes. The actual images here come from Coco, but then the objects and prompts are from RefCoco. And so here we can see a prompt referring to a specific plant behind Middle Woman. So it's a quite discrete, quite precise description, right? So we have several plants, we have several people, but then only one plant behind the woman. So behind the Middle Woman, right? So probably this one is a woman as well. So it has a different plant, which is quite useful, right? So we have this quite complex referring expression, and we'll let the model train on that. Another interesting concept is the so-called captioning. So in captioning, we, as label data, we take just the image and caption behind that. And you might get that from Coco dataset. There's actually a ton of sources of such image on the internet, like memes, Instagram, Reddit, all that stuff. Everyone likes to post an image and then caption it somehow. So there's quite a lot of data available there, but usually it's just an image and a caption. So there is no matching between specific parts of text to specific bounding boxes in the image. So what we can do is we can have previous version of Grounding Dino trained on just the label data like ref Coco or Coco with the serialized categories. We have this caption data, so just image and caption with no connection to localization of objects. And we also have this NLP parser, which is basically a Bert-like model that detects noun phrases. So from this text description of beautiful Caribbean sea turquoise, it might just basically select which of these parts of text correspond to noun phrases. And so what we do then is we have this initial Grounding Dino as a teacher model. We use that to detect bounding boxes for specific selected noun phrases. And we use that as a label. And then we train a student model to learn that and to predict these labels. So it's sort of weird bootstrap process, but researchers behind Grounding Dino and behind the model before that, which was called GLIP, they did ablation studies and actually proved that it works quite well. And they believe that it works well because it allows us to basically extract more information from existing teacher models. So, for example, look at this word turquoise, right? The model might never seen that word before in this sort of text to image fashion, but the Bert itself probably knows what it is, and it probably knows that it is some sort of color similar to like green or blue. So when the teacher model sees these noun phrase and sees this image, right, it can easily understand that turquoise, which is similar to blue, and it refers to this specific area. So it knows how the sea looks like. It knows that turquoise is close to the color of blue, and so it creates this explicit connection that this is how turquoise looks like. And thanks to this training, now the student model actually becomes better on this, because apart from just knowing how blue looks like or how a sea looks like, and knowing that turquoise is similar to blue, it actually now sees a specific example of turquoise, which is not exactly the same as blue. And by seeing the images, it basically understands it better now. And so we have this bootstrap process of teacher and student model, teacher model teaching the student one, which actually improves the quality without using any extra human label data. Now let's talk about results. So the easiest way to assess how good the model is to just try it out yourself. So I have a sample Jupyter notebook to do that. So I have an original picture from the Coco dataset. Everyone is more or less familiar with that by now. So I've loaded the Grounding Dino model, the main one based on Swintiny and Bert transformer. And I have my text prompt. And here I'm just trying to see how well I can detect a category from a list of given categories. So I load the image, I perform the prediction, and I save it as an annotated image. And so the result here, it's more or less fine. It's not really noticeable, but it also detects a glass as this entire picture. But then all the other detections are correct. That is, we tried something more interesting with the prompt like a sheep most to the right and see how well it works. Okay, that's a sheep most to the right, although it did highlight just a sheep here. Let's see if it works for the left. And doesn't. So sheep most to the left is still detected as the one to the right. So by just try it out yourself, you'll see that it works maybe in half the cases you would expect it to, which is not really good. I guess it's fine if you're doing like image generation with stable diffusion and you're actually observing the result in real time and you can adjust some things. But for an actual project, that wouldn't be sufficient. It also has this annoying threshold because now every query output basically outputs probabilities for every input token. And there can be several tokens highlighted with the same query. So you can just take max of them. You actually need some sort of threshold which introduces a new parameter to take care of. Really, it doesn't work as well as I'd expected, is what I'm going to say. So if we look at the actual paper, they state some results, zero shot on COCO detection. So zero shot, it gives them like 52, and then with fine tuning, it gives 62.6. So as a reminder, this is how numbers look like in COCO object detection. So current state of the art is 66. Original Dino, I think, had something like 63. Right. So basically what this tells us is that, the model is fine, right? So we do not lose anything by having this text to image cross encoding and all of that. If the model has seen the same data, it will be as good as the same model with just Dino, which just focuses on images. At the same time, if you do not fine tune on the data, it's much worse. Again, this is better than, a lot of other detectors from maybe 4 years ago, but not anymore. It's also completely different to how we've seen it happen to GPT-2, for example. So GPT-2 basically is a giant pre-trained model that beat a lot of state-of-the-art benchmarks without using any fine-tuning data. Basically saying that, this particular data set, this particular benchmark had a lot of scientists focusing on that and trying to come up with ways to improve the benchmark a little bit. And then GPT-2 comes along, not uses any data for training and just beats all the state of the art. This is not what we see here. Here we see that without fine-tuning, it's much worse than state-of-the-art models that we have. Well, I guess it is understandable considering that the model itself is not that big. So I've managed to run it on just my computer with one GPU. I don't have a giant cluster of multi-host, multi-GPU machines. So it's not the same, but still, I expected more, to be honest. They also quote results in different reference benchmarks like Odin W. So here they refer to the previous model called Glib a lot. And you can see like the entire history of zero-shot Odin detection on Odin. And it's really quite short, right? So we only see Glib and Grounding Dino here, which basically shows how niche this entire topic is compared to, say, just image captioning or image classification. So that one is enormously popular. You'd have models like foundational models like GPT-4 doing that really well. Unfortunately, they do not output bounding boxes. So this is what we have at the moment. My guess is that the architecture is fine, just that the training data used for the model is quite sparse. So the model itself is not really trained on that much data. Maybe we can just scale it up. We'll get like really foundational open set object detector that you can safely plug into your project. Right now, I think it's too early to do that simply because the quality is not that great. Nevertheless, I hope what we talked about today was useful because after all, these are all exciting concepts of image to text modalities, cross-modality models, and so on. So it was really interesting. This is the model I've been looking forward to describing for quite some time. In addition, I want to take a moment to advertise what else I have on my channel. So today we talked about Grounding Dino. I have a lot of videos basically building up to that that might help you in understanding of what's going on today about modern object detection like YOLO, Decoder, a lot of models from the Decoder series like Deformable Decoder, Dub Decoder, DN Decoder. I also have videos about reading source code for all of those. And the very next video I'm going to make will be about reading Grounding Dino source code. I also have videos about NLP. GPT-1, 2, and Bert, which are quite useful in understanding what was happening today. So the very next one will be reading Grounding Dino source code. For object detection, we also have this code editor model that is currently state-of-the-art, that is slightly better than the original Dino. So I'm hoping to make videos about that soon. Apart from that, I'm planning to start some videos about semantic segmentation and other exciting stuff in computer vision. So we have a lot to cover. Thank you, everybody, and see you soon.